Hello and welcome to Video Podcast 10.3. In this podcast, we will learn about ocean waves. By definition, ocean waves are energy traveling along the interface between ocean and atmosphere. The energy transmitted through ocean waves can end up traveling thousands of miles. It's important that you understand that when you observe waves, you're watching energy travel through a medium. In this case, the medium is water. Waves serve as visible evidence that energy is being transmitted from one place to another. There are some really important characteristics of waves that I'd like to overview on this slide. The first of which is known as a crest. And put simply, that's the top of the wave. The trough of a wave is the low point that separates two crests. The wave height is the vertical distance between the crest and the trough. The wavelength is the horizontal distance between two crests. You could also define wavelength as the horizontal distance between two successive troughs as well. And finally, the wave period is the time interval for one full wave to pass a fixed position. I'd like to call your attention to the wave particle motion shown in this image. For a given wave, the energy isn't just being transmitted at the surface. If we measure the wavelength for an ocean wave to be 300 feet, we'll see water movement down to a depth of 150 feet below the surface. In other words, water particle motion will occur to a depth of 1/2 the wavelength. I'd now like to discuss the factors affecting waves. Wave height, length, and period depend on wind speed, the length of time that the wind blows, and fetch, which is defined as the distance the wind travels over open water. Generally speaking, as the quantity of energy transferred from wind to water increases, wave height and wave steepness will also increase. In terms of maximal wave height, there is a critical point to be had. Eventually, the waves grow so tall that they topple over, forming what are known as whitecaps. There are two images shown on the screen that emphasize a really important concept that I'd like to spend some time on. Ocean waves can travel thousands of miles, which means that the energy they transmit can travel thousands of miles. But the water that the waves travel through doesn't travel very far at all. The water passes wave energy on to nearby water, and the water moves in a nearly circular path as it travels the energy along. I'd like to emphasize once more that when you see ocean waves, you're seeing energy being transmitted through a medium. On the screen, you currently see a video of wind blowing across a barley field, and this is a really great analogy for ocean waves. The barley itself does not travel across the field, but the wave does. This example is equally applicable to ocean waves, only instead of talking about barley, we're talking about liquid water molecules. The GIF you see on the screen is a great depiction of the science behind ocean waves. As the wave travels, the water passes energy in a circular orbital motion. You can imagine each one of those little yellow spheres as being a little water molecule. As the energy travels through the water, you can see that each one of the little yellow spheres moves in a circular pattern. Suppose that the wavelength in this case is 400 feet. Water molecules would move in a circular pattern to a depth of 200 feet, which is half the wavelength. But notice that the deeper you go below the surface, the less the movement of the water molecules. In other words, the water near the surface moves in a fairly big circular path, whereas the water deeper in the ocean moves in a much smaller circular path. That's because most of the energy transmitted by the wind affects water near the surface of the ocean. Our final consideration in this vodcast will be waves entering the surf zone. Ocean waves are unaffected by depth until they start to approach the shore. For this example, let's assume that we're dealing with an ocean wave that has a wavelength of 200 feet. What that means is you would measure a horizontal distance of 200 feet between this crest and this crest. With a wavelength of 200 feet, this wave extends to a depth of 100 feet because 100 is half of the wavelength. So long as the water depth is greater than 100 feet, these waves would be considered to be in deep water, and they would all be of constant wavelength. However, once that wave reaches a depth of 1/2 the wavelength, in this case, a depth of 100 feet, it officially touches bottom. And from here on out, the waves slow down and the wavelength decreases. In other words, the waves kind of start to pile up and get close together. You may have experienced something similar when you're driving on the interstate and you approach a traffic jam. As you approach the traffic jam, you slow down and the cars get a lot closer together. With ocean waves, the waves get closer together because the waves further from shore are moving slightly faster than the ones closer to shore. It's also important to note that as the waves slow down, they grow steadily higher in height. Once a wave is too steep to support itself, the wavefront collapses or breaks. Once the waves start breaking, we've reached what's known as the surf zone. Surf is defined as the turbulent water that's created by breaking waves. So in summary, when ocean waves are in deep water, they will have constant wavelength. But when they reach a depth that's equal to 1/2 the wavelength, they've officially touched bottom. From this point forward, the wavelength will decrease, in other words, the waves will get a little bit more bunched up, and the waves will also grow steadily higher as they slow down. Finally, when you start to see the breakers, you've officially reached the surf zone. Okay, that's the conclusion of this vodcast. In our next vodcast, I will discuss the tides.